let's take a look at the mass spectrum of benzene. Benzene has a molecular mass of 78 grams per mole, and indeed our molecular ion peak, which is the farthest one up, that is of significant intensity, is indeed 78. So that is our molecular ion, and it is in fact also the base peak. And so we'll see that because benzene, if it's lost an electron, it's still quite stable. That cation that's formed can resonate very easily. We don't really see benzene fragmenting as much, but that's not what we're looking at this time. What I want to focus on right now is this m+1 peak. So it's our normal molecular ion peak, but it has one more mass than our original peak does. And while we don't have the numbers on this particular spectrum, I can tell you that that peak is about 6.6% of the intensity of our molecular ion peak. And let's see how I know that's the case. So if we take a look at benzene, we saw that it had a mass spectrum kind of intensity peaks of 78 mass to charge ratio of about 100% intensity. So we always set it to whatever the highest is, that becomes 100. Highest intensity, not highest mass. And then we had a peak at 79 of about 6.6% the height of the molecular ion peak. And this is very important for us because we can use the ratio of these two as a way of determining how many carbons are present. Because we know that carbon 12 is about 98.9% of all carbon, and carbon 13 is 1.1% of all carbon. Carbon 14 is much smaller, like 0.00000000001% or something, so we don't worry about carbon 14. But the chance that we're going to have a carbon 13 present is 1.1 for every carbon that we have within the molecule. And so, by looking at this ratio here, if we since our base peak happened to be the molecular ion peak, coincidentally enough, we can divide those two. We can say, well, what is 6.6 over 100? Well, that's 6.6% if we just look. So, ratio-wise, it's 6.6% of the base of our molecular ion peak. And so, if we know that carbon 13 is 1.1%, and we have this extra peak that was 6.6% the intensity of our molecular ion, well, that can tell us the number of carbons in the molecule is going to be our 6.6% over 1.1%, which is 6. And so, that tells us we have 6 carbons in our molecule. Of course, this calculation would be slightly different if we didn't have 100% as our molecular ion peak. We'll take a look at a calculation like that in just a second. But for right now, this tells us the number of carbons in our molecule by looking at the ratio of the M peak and the m+1 peak. So that is this number up here is the m+1 over the M ratio, whatever those percentages happen to be. And 1.1% will always be a fixed number because that's the abundance of carbon 13 in the universe. So we're looking at that here. And so that tells us the number of carbons. Once we know the number of carbons, we can say, okay, well, 6 times 12, 12 would be our atomic weight of carbon, is 72. We have a molecular ion that is 78. So we have 6 left. Anything below 12, generally speaking, must be hydrogen. So we're going to have, therefore, 6 hydrogens in this molecule. So that tells us we have a molecular formula of C6H6. So generally speaking, when we're looking at determining the molecular formula from the number of carbons, the first thing we want to do is subtract the mass of the carbon out of the molecule. Whatever we have left, we're going to want to take a look at. For example, if we have nitrogens are easy to identify. Because they will lead to an odd mass to charge ratio for our molecular ion peak. If you have 1 or 3 nitrogens, if you have 2 nitrogens, you're not going to be able to see them very easily. So for that, you're going to want to look at something like IR or NMR instead to identify if you have nitrogens there. So if you have an odd number of nitrogens. Oxygens will be multiples of 16. And they are the most common other element. So nitrogen and oxygen are our most common kind of what are non-carbon and hydrogen, right? Carbons we get directly from the m+1 to m ratio. Once we know the number of carbons, we subtract it. Whatever we have left, we have to identify. We know there's going to be some number of hydrogens, but those we should take care of last. If we have some multiples of 16 in there, we may want to consider the presence of oxygens. And then, if we have an odd number, we may want to consider nitrogen as well. And so with the m+1 ratio, along with this information, we can get some more information about our molecule and figure out its molecular formula using the mass spectrometer. And so we'll take a look at another example here. Suppose we had a molecule has, let's say, a molecular ion peak at 20%, and an m+1 peak of an intensity of about 1%. Let's say we have these. If we take a look at our m+1 over m, comparing those two, we have a 1 out of 20 ratio, which is, 4%? I guess I should have been a little bit better with my numbers, but here we'll say 0.9. So here, 0.9 divided by 20. We'll represent this as a percentage, so that's 4.5%. So 0.9 over 20 times 100 will be our 4.5%. At that point, now we'll take this number and divide it by 1.1, which will be 4 point whatever. We know we can't have point whatever of a carbon, so we'll say that this is, we'll say it's going to be a 4 carbons present here in our molecule. And so those 4 carbons would give us a mass of 48, right? But let's say that we had a mass of 72. Our mass to charge, say, was 72. We have 4 carbons, so we'll subtract those 4 carbons. We end up with 12 minus 8, 4, 6 minus 24. Of course, we cannot possibly have C4H24, right? There's not enough bonds to do that. So let's consider another heteroatom. There's not room for a nitrogen here because nitrogen would give us an odd number, and 2 nitrogens would be 28. So there's no way that we can have nitrogen in this molecule. But what about an oxygen? If we have an oxygen, that would be 16, leaving us with 8 hydrogens. And that would be an acceptable number of hydrogens, right? We always have to think that hydrogens can never be 2n plus 2, right? Times your carbon. So the maximum number of hydrogens we can have for having 4 carbons is 10. That's it. So we can't have more than 10. So 8 is a reasonable number. That's why we couldn't have 24. There's just nowhere to put them. So there must be an oxygen in here. And then the rest we can say is probably hydrogen. And so we can say that our molecule here would have the molecular formula C4H8O. And this is an educated guess, right? We would clarify this by looking at other data. So NMR would tell us what type of oxygen we have, right? IR would also tell us. Do we have a hydrogen-bonded oxygen? Do we have a ketone or something? What do we have? We would look to other spectroscopy or fragmentation patterns. In our next video, we'll take a look at some halogens and what we might expect to see with m+2.